to just PhD at IMSC, like he said yesterday, and there's a very good chance he's going to give this talk looking at me now.
Nice one. Yes. Okay, so let us just start. So this talk is about QBF-Proof complexity, and my job is almost done by Beyersdorff by a very nice talk. And so this is about QBF. So let us just start with a very what QBF is. So first line is propositional logic. So propositional logic is, we know that the problem is given a CNF formula. We wanted to find out whether it is satisfiable or not. If it is satisfiable, you have to give a satisfying assignment for it. This is SAT NP complete problem. And what quantifier Boolean formulas does, it extends this by using quantifiers. They exist and for all. The meanings are, the semantic meaning is if there exists an x, this statement is true. If you plug x equal to 0, this is true, or x equal to 1 is true, right? And for all x means this has to be true. So to be precise, some examples that suppose I have encoded that x is equal to y. So for this CNF, two satisfying assignment is there, 0, 0 and 1, 1, right? So if you wanted to prove that it is satisfiable, you have to give 0, 0. Here is a QBF. I have just written there exists for all. So English meaning of this is, you are asking that is there exists a value of x such that for all values of y, x is equal to y. So by intuition, this is false. And similarly here, for all x is the exist of y such that x is equal to y, right? By intuition, this is true, but in QBF, we have to somehow prove it, right? So this is just a semantic meaning I have just written, right? So this is F2. This is a model of F2. So for all x means an AND gate. For all, there exists y is an OR gate. And you wanted to, for every x, you should get a value of y. So these green lines are, so this is a model. And here is a counter model. The exist x is an OR gate, for all y is an AND gate. And here you wanted to say that for, if this is a counter model, both has some counter. This is a counter model, right? So somehow for QBF, some assignment tree is there. For propositional logics, assignment is there, right? So somehow this is maybe difficult. So this is a notation. Let us just fix a notation before going. So our QBF will look like that. First is quantifier prefix and then a CNF formula. And this each QI is either will exist and for all. Xi is a pairwise disjoint. And yes, Xi is not equal to Xi plus 1. They are alternating. If a variable x belongs to xi and qi is an existential quantifier, I will say that x is an existential variable. Similarly, if x is belong to xi and qi is for all, I will say that x is a universal variable. And left and right is also well defined. So if x is in xi, y is in xj, and I is less than j, then I will say that x is to the left of y in the quantifier prefix. Similarly, y is on the right of x. And one set is very important for, suppose u is a universal variable. I will say that all existential variable to the left of u is denoted by this set left of u, L of u, in that quantifier prefix.
Can I just, is it okay that, I mean, I don't think it's nothing.
Yes.
So are the identical type of quantifiers commutative? They are.
So you are saying that for all x, so they are different meaning, I said, right? So there exists for all. Okay. They are same. So therefore, this capital X may have several variables. Capital X1 has several variables. They exist. Then for all.
Alternating.
Yes, alternating this. This is alternating. There you are talking about sigma 2, sigma 3, and so on. So any other doubts? This is just a basic. As what I have said, this is nothing but a two-player game. So at ith iteration, QI player, existential of universal, right? He is setting values to xi. And an existential player wins if at the end the assignment that you have created is satisfying the CNF formula. Otherwise, universal player will win. So I can define a strategy for a universal variable. So what is a strategy? It is a function. It has to give values u to 0 and 1, right? And what is the domain? All existential variable to the left of you. So for all assignments, this strategy should give me 0 or 1. And I will say that this strategy is a winning strategy for universal player if whatever however existential player will play. Universal player, if uses this strategy, will win the match. Right? So this, and we know that this is p-space complete. Even existential player will win or universal player will win. We don't know. They are all NP complete. P-space problem, P-space complete problem, which has been proved just after Cook theorem of P-space complete. P complete, right? Cook theorem. Just after that, Mayer and Stockmar has proved this. They are the one who also initiated polynomial hierarchy, that in 1972 maybe. A very quick example of winning strategy, right? Equality formula. Olaf has already presented this. They have defined this in their paper to establish some lower bound technique, right? So what is that equality formula? This is a formula that exists for all and there exists T. Some clauses are there. Let us prove that this is false just by giving a winning strategy. Winning strategy is nothing but UI will play as Xi. So once existential player will play, the universal player will turn, it will just set UI to Xi. And why this is false? Because after universal player will play, existential player turns will come, right? You will see that from every I, either only Ti will remain. And then existential player has to give all Y's. But once he did that, B will be falsified. So this is a winning strategy. So in this talk, winning strategy is very, very important. Therefore, I have just again equality formula, and this formula also we will use again for this talk. Here is a broad landscape. Olaf has already come and told Q resolution, QU, CP plus 4 all red, Frege plus 4 red. Only this merged resolution he has not touched. Maybe because you wanted to touch it here. So, so in this talk, there is a proof system. I will define what merged resolution is. This will be very different from all what Olaf discussed about for all reduction and all those stuff. And in this talk, we will extend this to a family of proof systems. And we will give some lower bounds on regular, we will give some separation results and so on. But let us just start with merged resolution itself. At what? So MRes is a proof system for QBF. It is a sound and complete proof system. Completeness is very important for a proof system. It means that if you have a false QBF, then you must have a proof, maybe MRes proof of the fact that F is false. This is called completeness. And soundness is also very important. If you have a proof for a QBF in merged resolution, then that QBF must be false. And one more thing is that it should be point time verifiable. You should not just give a proof. It should also be a proof so that other algorithm will verify it, that this is a correct proof. So merged resolution has all these properties. The idea of this is it will build that winning strategy step by step. It will build a winning strategy, right? And then it should have a winning strategy. And if it has a winning strategy, it has to store it. Some data structure you have to use. So they have used merge map, which is very simple branching program. Any doubts so far? So the question was that why only merge maps? Can we use some other representation for strategies? The other question is, can you give me a framework in merge resolution style where any representation I can use at the end? Some framework, right? So we have a complete representation means if you have a function, decision function, which is finite, in this representation, you should have a representation. That is what complete means. And the question is, yes, we have defined MRes-R proof system, which we are going to define. So, any doubts so far? So let us just begin with MRes-R definition. In the process, I will also tell what merge resolution was. So suppose I have a QBF, false QBF, and I wanted to derive a line LM. So the derivation looks like that L1, L2, LM, where each Li looks like a clause Ci, and for every universal variable U, there is a strategy I have to define, right? And how each Li we are defining, only two rules are allowed. One is axiom rule. Axiom rule, let us explain by example only. So this is a clause x1 or not of u1 or not of x2, and what was this ci? Just take the existential subclause x1 or not of x2. I have taken that. For universal variable, you just see the falsifying assignment. So here if I will keep u1 to 1, this not of 1 will be 0. So therefore, the strategy for u1 is 1. And u2 is not here. The strategy of u2 is star, don't care. Similarly, for this, I have downloaded x1, not x1 or x2, and the strategy u1 is star and u2 is 0. This is example. This I can always do in merge result in MRes-R. The second rule is resolution rule. For that, suppose I wanted to derive Li using two lines LA and LB. So I can only, it is in negative probability, B prime. This is x is a pivot, an existential variable. And now, again, either x is on the left of you or right of you. So if x is on the left of you, then when universal player is playing, x has already been played. So therefore, we are just using it that if x is 1, you take HBU. So x is 1 means this is falsifying, right? Just go and take that strategy. If x is 0, so x is 0, this causes CA prime, right? You just take HA prime, HAU. So this is if else. So in this, if x is on the left of a universal variable, you just take if else. Based on the value of x, you do one side. Okay. Now, if x is on the right of you, that is when universal player is playing, existential value he doesn't know, right? In the two-player game. So now he will going to use the strategy that he has built so far. And he said that, okay, my strategy for this u, which is to the right of x, or which x is to the right, u, when I am playing u, x has not been played. So what I will do, I will just check whether these two strategies for you already that are they consistent. I will tell you what consistent is. If they are consistent, take the union step. Union also I will tell. Just it is set notation only. And merge resolution also does some tricks here only, right? Maybe I will just skip that. This strategy is over, right? And when pi is refutation if the last was in an empty clause. So this proof system is okay, right? I think strategy, whatever strategy is, only the point is consistency checking, union, if else. This should be efficient in your representation. If it is not representation, then positive verifiability will not work, right? I will come to an example also, an upper bound of that. Let us go with if else, consistent, and union. Three operations I have to define, right? Then it will be clear. If else is very simple. If x is 1, go to the first strategy. If x is 0, go to the second strategy. That is if else, right? I wanted to define when two strategies are consistent. Let me define when two assignments are or partial assignment are consistent. They are consistent. So for suppose here two assignments are there, delta and epsilon. If they are not pointing to don't care both, then for every f they should match. Consistent means that. For example, these two assignments are consistent because for x1 it is giving 0 and another is giving don't care. No problem. One is giving star, x2, this is 1, no problem. x3 they are both giving 1. So consistent, two partial assignments are consistent, is clear, right? I think. Similarly, when I will say that two strategies are consistent, so for a universal variable, when two strategies are consistent, if whatever your assignment is giving, right, they are consistent for every possible assignment to the existential variable left of you. And what is union? So I can always view an assignment as a set which their literals are satisfying. So for example, if epsilon of x is 1, I will take x. If epsilon of x is 0, I will take not of x. And now union of assignment is also very well defined. So this all things have already been done in SAT 2021 paper. They are designing an algorithm for DQBF. The paper name itself is QBF solving for using resolution. So all this thing has been defined there only. Soundness, for soundness, this trick is not out. This is the well defined trick that at the end we have an empty clause. At the end line, if I will prove that the strategy that my proof system has defined is a winning strategy for universal player, then definitely the initial QBF is false only. And for completeness, what we did is, so any representation was allowed in our MRes-R definition. Let us use merge as a representation. So call that function, call that proof system as MRes-M. We have showed that MRes-M P simulates merge resolution. In fact, every merge resolution is an MRes-M proof only because they are isomorphic and here consistency. So we that M can P simulate merge resolution. And now MRes-M is complete now. Now, given an MRes proof, I have to convert into MRes-R proof for any representation, complete representation. But the complete what? This proof has strategies as a merge maps. They are just functions. These functions definitely be sitting in that complete representation also. So this problem is decidable. You have to search that. So therefore, now we have shown that it will take time, but this proof system MRes-R is also complete. So I said, right, two things are very, very important: soundness and completeness. One thing I said that verification is also important. So because of this consistency check, all these proof systems, right, are non-polynomial verifiable. Representation can be arbitrary, where consistency checking is very difficult. But thanks to the knowledge representation, what we will go there. There are representation where consistency checking is efficient. But anyway, the problem is clear. The proof sum is also clear. Let us. So I said that we have a lower bound and we have a separation also, right? So for regular MRes-R is exponentially stronger than regular MRes. This is what our result is. Let us understand what regular means. So any proof system, I've just defined it as a sequence of lines, right? We can also draw a DAG out of that, where maybe hypothesis is pointing to the conclusions. In that DAG, I will say that DAG is regular. If you check any route to leaf path, every variable from X is used as a pivot at most once, then such proofs are called as regular. And if X regular means it is a regular. All existential variable in any route to leaf path, at most once you can use it as pivot. So for separation, we have used that squared equality formulas only. So let us just define what squared equality formulas are. So equality formula we have already done. Squared equality formula is just two-dimensional setting of equality formula. Here so I have two variables. Winning strategy is exactly that UI play as Xi and universal variable Vj play as existential variable Yj. Again, this is a winning strategy because after universal player is played, from every Ij, only one of this Tij will remain. And then existential player has to give one to all, and then again capital B clause will be falsified. So this is a winning strategy. This is a false QBF formula. So we wanted to, and this equality squared equality formula is easy for regular merge resolution. So what Mahajan and Beyersdorff, they are here only. So what they did is they carefully removed universal variables from the clauses Aij's in such a way that my QBF will be false. That is, the winning strategy will be as it is, but it becomes harder for regular MRes. And for that, they have used very simple trick that suppose an n cross n grid is there, we will convert it, or we will partition it into two regions, capital R0 and capital R1, in such a way that every cell, so every region must have a cell from each column and from each row. From this, suppose I have given some two regions, R0 and R1. Based on two regions, let us see how we will remove the universal variables, right? So regions is clear, right? With n cross n grid, two regions I have defined in such a way that every cell, so every region has a cell from one, at least one column and from at least one row. Such a region you give, and now here is how we are removing our universal variables. So B is as it is, quantification is also as it is, only clauses. So if Fij belongs to R0, here is how I am removing. So here I have removed Vj, right? Here I have removed Ui, and so on. And if Ij belongs to R1, this is how I have removed both Ui and Vj. So this is very carefully they have defined. Square equality with holes, they call it. So any doubt in this? So again, the universal play strategy is exactly the same. Ui will play like Xi, Vj will play like Yj, and they showed that this is hard for regular merge resolution. And we have given an upper bound for, yes. No, they are not for two players. Yeah, they are not for two players. I just, yeah, so there is square root formula, which is easy for regular merge resolution because they are all isomorphic. I will just tell where it will not work. So they wanted that the regular merge resolution proof should not go through. So carefully they have to remove some universal variables. So Mahajan should did that. You can ask them better, right? So and what we have done is that we have just given an upper bound on our regular MRes-R proof system. So while upper bound, I will tell you where that will get stuck. So this is a proof. I hope this is visible. So suppose Ij belongs to R0. For each Ij belongs to R0, I will define this Tij. I will derive this Tij, right? And this variable, I will resolve on Xi. Xi is to the left of universal variable. So by rule, I have to do if-else statement, right? And for if-else statement, we have no condition whether they are consistent or non-consistent. Based on X, you just go to one side. That's what we have done. So if X is 1, you have to go this side, right? Because here it was 1, not 1 is 0. And here you can say that if X is 1, Ui should be star. Yes, if X is 1, Ui star. If X is 1, if X is 0, Ui to be 0, right? This is what we have written. So there is nothing but if else. Not much, right? No consistency checking, nothing. If else. Similarly, this here also Yj is to the left. So again, if else. You will get some because we are dealing with arbitrary representation. We can solve some, means we can simplify this. Anyway, we have to use some claims and all, but believe me that actually the strategy for this Tij is this only, that Ui is don't care for Xi and Ui is 0 for Xi, not of Xi, and similarly for Vj. For K, what happened? Okay, so for KL belongs to R1, again we have to define that. Again, if else statement is there, believe me that you will get this strategy. If else, you just go, right? And now our task is to get an empty clause. So you just start with B, capital B, and for all Ij belonging to R0, you just go on resolving them. Here we have to be careful because now this Tij is to the right of universal variable, right? Now they have to be consistent. Or if one is a trivial strategy, then they are consistent only. So here one is always a trivial strategy, up to B of B minus R naught, means B minus all Tij's, Ij belonging to R0. There one is trivial strategy, one is you just take that, right? Because if they are consistent, you are taking union. So one is star union 0 is 0. You just take that, right? And after that, we have to be careful. Merge resolution, regular merge resolution will not go through it because now they become non-isomorphic in terms of merge maps. They are different, but here we don't want isomorphic, we want consistent. So somehow we have proved that they are consistent, everything will go through in a claim. Yes. Okay. So now our last topic is we have also proved lower bound on regular MRes. Right? So that we have used CRN formulas, completion principle formulas, and actually this was known to be difficult. Lower bound has already been established with regular merge resolution in Mahajan and the hard QBF for merge resolution paper, and we have just seen that we can lift that lower. So what is this completion principle? Suppose we have A1 to AN and B1 to BN. Two sets are there. Depict them as their as a table where for every A1 we have a B junk. Every A2 we have a B junk. Right? This is a table. And what is a player? So player 1 has to come from each column. Either he has to exactly delete one cell. From each column he has to delete exactly one cell. This is what player 1 will do. Player 2 will come and choose a row, either top row or bottom row. And player 2 will win if whatever row he has chosen contains every A or every B. So this player 2 has a winning strategy for sure. And the fact that player 2 has a winning strategy in this game is called completion principle. So let us just quickly 1 minute. So player 1 will come. He has deleted exactly one cell. Player 2 will come. If some AI is missing from the top row, then definitely all B chunk is in the bottom row. Just choose bottom row. Otherwise, all AIs are present in the top row. Pick the top row. And what CRL formula does? By this encoding, it is just false QBF we have to find. So it has to somehow encode that player 1 has a winning strategy. So if you do that, then encoding is not so difficult. But now this is false because here my encoding is saying that player 1 has a winning strategy in this 2-player game. So this is false. And the lower bound technique is also very simple. This was regular. The idea is nothing but suppose this is a regular proof. All axioms must contain all AIJs by definition. The empty clause does not contain the AI any variable. So definitely there is a part of my proof that is S prime without A union B variables. This S, capital S, is the boundary of S prime. The lines in S prime does not have A union B variables, but the hypothesis has. Such an S I was looking at. We will prove that every clause in this S, the width, the number of literal in it is at least n minus 2. Once I have proved this, the lower bound is over. Because this is actually an unsatisfiable. This all C, if you consider all this C, this is an unsatisfiable formula. Every square variables, every clause has n minus 2 literals. So every assignment has to put n minus 2 zeros there. So the number of assignments falsifying a clause from S is at most 2 power n square minus n minus 2. The overall clauses are 2 power n square. Every clause has to every assignment has to falsify a clause. So the number of clauses has to be big. And that we have for n minus 2. Number of clauses are there in S, and therefore pi also have that many clauses, right? 2 minutes. I said that at the end I will come back to knowledge representation, knowledge compilation. I said that consistency checking in general is means it is hard for consider, but there are like ordered binary decision diagrams. For that, consistency checking is easy. And if you allow only ABDD representation in our proof system ordered, then they are called verifiable. Some last, so this is what I have shown. There are so many other stuff that I have just avoided. But here is a open problem that we have. So there exists a family of QBF which are easy to refute MRes-R but are hard for merge resolution. So suppression is only for regular. In general, is still open. And thus there exists a family of false QBF which are hard to refute in MRes-R itself. So these two. Thank you very much.
Hello.
I'll let you know like 5 minutes before.
Okay. Sure. Thanks.
Okay, welcome to the second talk of the session. Speaker is
forward this
the
for
School of
the
Management
for the
at
point.
University.
Hmm.
Till not too long back, she was a grad student here, PhD with Beyersdorff. Her research interests are in themes at the intersection of algebra and computation. So that.
Yeah, thank you so much for the introduction. Yeah, thanks a lot to all the organizer for giving me an opportunity to talk here. Yeah, so I'm going to talk about optimal representations of finite groups. So basically, we will see two algorithms for two different group theoretic problems. So yeah, since we will talk about group theoretic problem, let me tell you how the group representation, like how do we give a group to an algorithm. So there are few representation. For example, there is this generator related representation where we have given a group by its generating set, and we also have a set R which is a relation on the generators. And there is this representation known as scalatable representation where we have given a group G explicitly by its table. Also, there is this permutation group representation where we have given a group G. It is a subgroup of Sn and it is given by a generating set like permutations in Sn. So if you notice for scalatable representation, the input size is if the order of the group is n, then the input size is order n square or poly in n, and while in the permutation group representation, the order of the group could be n factorial, but to represent the group, we just need few permutation from Sn. So in that sense, it's very efficient. So yeah, that is the group representation. Let me first go to the first problem that we will see. Okay, so it is called minimum generating set problem. So a minimum generating set, or first let me define generating set. It is a subset of a group. Okay, thanks. So it's not working. Okay, so a subset T is called a generating set of a group if we can represent every element of a group by elements of T or their inverses in a finite product. And a minimum, for example, for Sn we have a generating set of size n-1 and also of size 2. A minimum generating set is a generating set whose cardinality is minimum, and that cardinality is denoted by dg. So for example, for Sn, d of Sn is 2. Yeah, so the problem is defined as follows. We have given a group G by its Cayley table. For simplicity, we are assuming it is given by Cayley table. And we are interested in finding the minimum possible size of the generating set, which is dg. So one could give a trivial algorithm. What we can do is we know that there is so for every group we can find a generating set whose size is at most log mod g. So this will give us an algorithm which will run in quasi polynomial time in the order, because we can try all possible subsets of size at most log mod g. Yeah, so before going into the algorithm, let me tell you some curious thing about this d value of g. So there is a simple group. It is a group without normal subgroup. So a simple group, it is known that it is generated by two elements. So d value of S is bounded by at most 2. Now, let us consider the most simplest non-abelian simple group. It is A5. So it is known that if you take the direct power of A5, like 19 times, then also its d value is 2. Now, if you take it for 20th power, then its d value will increase just by 1. But even more surprising, even if you take such a large power of A5, the d value will increase just by 3. So it's now 5. So that is also one motivation to find an algorithm that can find a minimum possible generating set. So that we can represent such a large group with just 5 elements, or in general the minimum possible generating set. Okay, so there are a few results already known for this. So people have studied this minimum generating set problem before. For example, Arvind and Toran, they have showed that this problem for Cayley table, it's in D space log square mod G. And Lucchini and Menegazzo, they have given an algorithm that works in polynomial time for solvable groups. So in the paper, they have not analyzed the running time of the algorithm, but if one can see, it is easy to see that it is in polynomial time. But the following question was still open, that can we design a polynomial time algorithm for arbitrary finite group, which is given by its Cayley table. So what we have shown is the following, that we can have a polynomial time algorithm that can compute a minimum size generating set for the group in polynomial time. And so this theorem also finds one minimum possible generating set. So it is a search. It also solves the search version of the problem. Yeah. So I'll go into the algorithm, but before that, let me mention few things. So there is a theorem by Gashu and Lucchini. What it says is that suppose we have a minimal normal subgroup N, and suppose we know the minimum generating set for the quotient group. Then we also have a bound on the minimum generating set size for the actual group. So it will be at least L and at most L plus 1. And moreover, it also says that if it is L, then we will be able to find one of these mod n to the power L tuple. We will be able to find one possible generating set of minimum size. And if not, if DG is not L, then again we will be able to find one possible minimum generating set by tying all such tuples. But if you see, the running time of this algorithm is again quasi-polynomial time, because n could be size of G. Okay, so that is what we have shown, that what we can do. So for if n is abelian group, we can use the result by Lucchini and Menegazzo to handle this case. So the most non-trivial thing would be, how do we handle the non-abelian minimal normal subgroup? And that is what we shown, that if n is non-abelian minimal normal subgroup, then we can actually reduce the search space from the above theorem. So we take T to be equals to this special number, which is order log mod G, and we show that if T is less than or equals to L, then there is a generating set of G of this form. Yeah, so we just have to tie mod n to the power T many possibilities. So that is the algorithm. It's really easy. So what we can do, we first find a minimal normal subgroup, say n. It is already known, so we use that as a black box. And then we recursively have a generating set for the quotient group, G quotient n. If n is abelian, then we can use their result, and it is very efficient. So we just have to try at most log square mod G many generating set. Now, if n is non-abelian, then by that result that we have seen, we can tie such tuples of modern power total modern power T many tuples. We will be able to find one of the generating set. But what if T is not less than or equals to L? So here what we have shown is that in this case, D value of G will be always bounded by L plus 1, and L plus 1 is bounded by T. So we can afford to try all mod n power L plus 1 many tuples in this case. So that is giving us a polynomial time algorithm. So this algorithm is very simple, but the proof of correctness uses a lot of group theoretic like counts of finite groups and other things, like shift series of a group and all these things. And also the T value we take, it is bounded by log mod G, but if we take the exact value which we take in the paper, we could reduce this order 1 to 6 or so. Yeah.
Given a set, how do you check if this is a generating set or not?
Yeah, that is known to be polynomial time. So it is actually, you can use membership testing. even for permutation.
And this, the complexity is polynomial time regardless of the size of the set we have.
Yeah. Yeah, so we took a Cayley table in the problem definition, but this algorithm also works when the group is given by permutation group representation, but then it is polynomial in the order of the group, which is not in the input size. Okay, so that is the first thing. Yeah, whether it is generating a group. The smallest one we want to find. Any questions? Any other question?
Later,
What is related?
related the term.
Oh, okay. So that is a like a relation. So you have given a generating set, say T, and you have some relations on those generators, like commutator. For example, 2 generator will commute. So that is a relation. So like list of such relations. Yeah. So using that representation, you can even represent infinite groups, like free groups and all this, quotient of free groups. Okay. Okay, so most of you will know, most of you will know Cayley's theorem, right? It is saying that we can embed all finite group into some symmetric group for some n, but what we can ask, what is that minimum m, so that we can embed given G in Sm. So that is the known as minimal faithful permutation degree in mathematical literature. We denote it by mu G. And it is easy to see that mu G is bounded by mod G. Okay, so the problem we defined is as follows. It is called minimum faithful permutation degree problem, or in short, mean per deg. And here we have given a group G by a permutation group representation. So we have an access to a generating set T. Sorry, we have given a generating set T, and we want to find mu of G. So there is an equivalent definition of mu G, which I will not go into the detail, but you can see that using this definition, we can have a very inefficient algorithm to find mu G for a given group. And it is not efficient, but yeah, we have some algorithm, because we can find all the subgroup and also we can find core of the subgroup H. Yeah, so okay, sorry. Okay, so that is the problem. So this problem has been defined in paper by Cantor and Lux in 1990, and show that this problem is in NP. But what they have mentioned is that other than NP, if someone want to solve it for like special classes of group, someone has to come with new mathematical tools, because yeah, existing algorithm will not be that useful to solve this problem. And what we have considered is also some special classes of group, which is known as semi-simple groups. Yeah, so what we have shown is that we have given a group G, which is semi-simple. By that I mean it does not have any abelian normal subgroup. So then what we have shown is that there is a randomized polynomial time algorithm that can compute mu G. Okay, so why we are interested in such groups? So it contains a lot of interesting classes of groups, but above that there is this group theoretic community who are working for group isomorphism problem, and for them also these semi-simple groups are really helpful. And also there is a known algorithm for like polynomial time algorithm for group isomorphism for such classes of group. So that's why the first point was like that's why we started with semi-simple groups. Okay, so now I'll say a brief idea of the algorithm, randomized polynomial time algorithm. So we have used this theorem by Kennen, Holt, and Unger. So let me first define this thing. So we have given a group G, and we have a minimal normal subgroup, say N, which is a direct product of simple group. Now we can define an action of normalizer of S1 in G on S1, which is let's say phi. Then what we have defined, mu of G comma N is mu of A. So A is the quotient group which we will get from, so which is an image of phi. So it is normalizer quotient kernel of phi. Now, okay, so we define mu of G comma n to be equals to mu of A. So it is easy to see that A is an almost simple group, but what is more important is that A is a quotient group. So it is normalizer of S1 in G quotient kernel phi, right? Because it is an image of phi. So since we are working with permutation group representation, it is difficult. Sometimes it may be difficult to work with quotient in permutation group representation because like the quotient may have arbitrary large degree in terms of the actual group. So here we cannot have access to the quotient group A, or I would say access to a generating set for the quotient group. Yeah. So, but what they have said is the following, that if we have a semi-simple group G, then suppose circle of G is N1 to Nr, it is group generated by all the minimal normal subgroup of G, then mu G is the sum of Li times mu of G Ni, and mu of G Ni's are nothing but mu of Ai as we defined above. So this theorem actually says that we can reduce finding mu of G to finding mu of A, but the AIs are what we have obtained from the definition. They are not arbitrary almost simple groups, so we do not have an access to a generating set for the almost simple groups. So this is weird kind of reduction. It's not actually a reduction, but yeah. So now, okay. So from here it is clear that to find mu of G, we have to find mu of A for almost simple group A, right? Now they also gave a result that they also proved this, that if A is an almost simple group, then mu of A is equals to mu of S, the simple group S, except for few cases which are in this table. So if you see this table, first 8 or first 9 groups are constant size, so we are not interested in those things, but the remaining 7 groups are really like infinite. Those are infinite families of group, and that is what we have to decide. Like if we want to find mu of A, so we have to decide whether our S comma A pairs belongs to this table or not, and that is the most difficult part of the algorithm. How do we first decide whether our S belongs to the first column, and if we are able to find which of the 7 group we have, like which of the simple group we have, the difficulty would be how do we check whether the corresponding A will satisfy the second column. Okay, so that is the that is what we are doing in randomized polynomial time, checking from this table. Okay, so our goal is to find mu of A. Now, so there is a randomized polynomial time algorithm already known, which is from Cantor and Serres, that can recognize a simple group which are classical simple groups. Like if you see the table, the first 4 simple groups are classical simple groups, so we can recognize those simple groups using their algorithm, and that is randomized. So we use that as a black box. So our algorithm is also randomized. Other than that, it is deterministic. Yeah. So. And also the remaining groups were of order less than n to the power 8 because they are small size group, Lie type groups. So we can at least using this black box, using this as a black box, we can recognize whether our S belongs to the first column or not. Okay. So that is what we can do, but now we have to check whether the A belongs to the second column or not, third column or not. Okay, so I'll not go into the detail of all the cases, but let us see the easiest or not easiest, but the first case where we have S1 is isomorphic to PSL, the first group. Okay, so the row look like this. We have to decide whether our A set is A is a subgroup of P gamma L DQ or not. Okay, so what we have done here is that we already know that our S1 is isomorphic to PSL, and we already have that isomorphism map, which is also we got from Cantor-Serres algorithm. Now, what we will do? So, if you notice, this A is actually a permutation group, like it is permutation, it can be seen as a permutations, but this P gamma L DQ or PSL, all of those groups are matrix group. So can we somehow use the structure of matrix group? So that is what we have done. Like we first transfer our permutation group representation of A to matrix group representation. So we go from PSL, like automorphism of PSL, and then from automorphism of PSL to automorphism of SL. So now SL has a really good structure that we can use, and that is how we define, we have this lifting algorithm. So usually such lifting algorithms might not be easy, but fortunately it worked for us. So yeah, for any automorphism, we lift it to an automorphism of matrix group. And so that is this A prime, like new A prime, which is now a subgroup of out of SL. Okay, now our task is to see if A prime is contained in P gamma L DQ or not. And P gamma L DQ is a special subgroup of SLD or SLDQ, which contains all the automorphism which does not have some specific type of automorphism in its decomposition, and that are known as graph automorphism. So what we have to check is that given an automorphism, can we recognize whether it is a what type of automorphism of SL it is, like in automorphism diagonal field or graph automorphism in its decomposition. So we first have to find its decomposition, and then we have to see whether in its decomposition whether there is a graph automorphism or not. And that is where we have this recognition algorithm where we are recognizing the type of the automorphism, and these uses tools from representation theory like Schur's lemma and also Gaussian elimination algorithm. Yeah, so we take some special type of composition of automorphism, and we are checking whether this automorphism is inner automorphism or not, or diagonal automorphism or not. And if it is, then we know that the F is field automorphism and G is graph automorphism. So we can check whether in the decomposition of alpha, whether graph automorphism is present or not. So that is how we can decide whether A is a subgroup of P gamma L DQ or not. That is the first case when S1 is isomorphic to PSL DQ, but we have also handled all the cases from the table, and so we can also decide, we can also find mu of G comma N. And once we find mu of G comma N, we can use the result by Cantor, Cannon, Holt and Unger to find mu of G. And that is randomized polynomial time algorithm. Okay, so before I state open problem, I'd like to say something like why we are interested in such algorithm, like such group theoretic problem. So one motivation could be a group isomorphism problem, because it is a special case of graph isomorphism problem, and we do not know any polynomial time algorithm for graph isomorphism problem, but it is believed that we can at least put group isomorphism problem in P. So that's why we also study other similar problem, and can we design polynomial time algorithm for for such problems which have which can be used to solve group isomorphism problem. So that is what, so there are few problems which we can state, like so our work is for semi-simple group, but can we also do it for other special classes of groups? But no, the most interesting problem, at least to me, is the following, that can we have some relation between mean per deg and graph isomorphism problem and group isomorphism problem? So that is the open problem. It will be really good if some of you could work on this. Yeah. Thank you. Any questions? Yeah.
I mean, like, for example, there was a table where there's a whole bunch of special groups where, I mean, some of these parameters seem to be equal. Like, are there, I mean, is there, for example, are there any of these groups where the group isomorphism problem with the promise that the two groups are one of these types?
Okay, yeah.
Is it easier in those
Yeah,
situations?
to be polynomial time.
Oh, there it's known to be polynomial.
That semi-simple group is known to be polynomial time given by its Cayley table, of course.
Okay.
The groups are given by its Cayley table and they are semi-simple, then it is known to be polynomial time. And all these groups are semi-simple.
Okay.
So it
Okay.
even for
Yes.
more general groups which covered all the groups from this table, it is known to be polynomial time.
And is the Cayley table, can one recognize that, I mean, the given Cayley table corresponds to one of these things? I mean, that is recognizable in polynomial time?
Yeah, whether it is semi-simple or yeah.
Like, whether it's semi-simple, that is also recognizable in polynomial.
Yeah, that is also recognizable.
Okay.
These are simple groups. So the counting group also cantor, you can apply cantor. Cantor says to, so these are simple. So first column, these are simple groups. So for simple groups, I think you can do the recognition.
Not technical question.
Okay.
So, how do you get all the L's and capital case I's to appear as bold? Is that a correct choice? So in almost you can see the L looks bold. I don't know if it's a correct choice or something.
Maybe it's my mistake. Maybe I don't know. I haven't done it intentionally. Yeah, I don't know if it is really bold, but yeah, I haven't done it intentionally.
Maybe it's not the right side problem.
Yeah, maybe, yeah. I'm not sure.